Mm-hmm.
Yeah, seems to be working. So, topic for the day is the Quantum Fourier Transform.
Yeah.
Or QFT as it's usually abbreviated. And what I'd like to do, because I'm the kind of guy who, in order to understand something, I really need to kind of play around a bit with it. And the Fourier transform itself is one of those things that pops up everywhere when you study physics. But I never really kind of got to grasp with what exactly it is until fairly recently. I just knew that, okay, if you want to do signal analysis, you have to use a lot of Fourier transforms and stuff like this.
Yeah.
Like finding frequencies and stuff. That's kind of the intuition I had, right? If you have some very big noisy signal with a lot of frequencies stacked up on each other, you can kind of Fourier transform it, and then you'll get these spikes that represent the different frequencies. And that was my level of understanding of the Fourier transform until recently. So the Quantum Fourier Transform is interesting because it runs in big O of n squared, where small n is the number that you input, which is no, it's not the number, it's the length of the number. So if big N is the number itself, it is written with 2 to the n bits, right? So if in relation to the number itself, it runs in order log big N squared, like this. It is actually, it does not speed up the fast Fourier transform on classical data. So on classical data, you have the fast Fourier transform, which I think runs in n log n, but I'm not sure. But the entire difference is, of course, that quantum states are exponentially bigger than classical states.
Yeah.
So if you input big N 2 to the n, this becomes like 2 to the n log 2 to the n, which means that using the fast Fourier transform on quantum data would take you n 2 to the n time to do, which is exponential, and that's like the big difference. So these are actually the real numbers that you have to compare. But if you only have classical data, you can't speed up anything, essentially. First of all, to prepare an exponential amount of data for transformation would already take an exponential amount of time, and also to measure the results would take exponentially many measurements. So you have to, it's a bit more subtle than that. So that's kind of the idea of what a quantum Fourier transform is not. What it is something that can work globally on the entire internal state of a quantum computer simultaneously, allowing you to do stuff with the internal states that you couldn't do classically. And then if you're very clever about it, this will allow you to solve problems like factoring with less than exponentially many measurements. And so that's the idea. I would like to kind of start over. So can I wipe, or are you still writing? Yeah, Yeah.
For me.
Okay. So if I start wiping anything and you need me to stop, then just tell me. Okay, so the Fourier transform looks like this. Okay, so first of all, I will always use n equals 2 to the power n, where small n is the number of qubits we have, while big N is the input number that we're working on. So yeah, you know how this works, right? So for n equals 3 qubits, you can get from the number 0 to the number 7, etc. Okay, so you get a sum, and this is k equals 0 to big N minus 1, and an exponential 2 pi I j k over n k. So this is the Fourier transform. This is how it looks. And so the first part of this talk, I will just try to see what happens if you Fourier transform different kinds of states. To start off easy, I'd like to Fourier transform the 0 states, just to see what we get. So this is then 1 over square root of 2, because there is only one qubit, so 2 to the power 1 is 2. And then the sum from k equals 0 to 2 minus 1, that's 1. E to the power 2 pi I. J is 0 times k over 2 k. So since this is 0, this entire thing becomes 0. So we get a sum from 0 to 1 of k, so that's 0 plus 1, and then divided by square root of 2. And notice that this is the Hadamard transform of the 0 state. Similarly, we can do the same for the 1 state, just writing up same stuff again. E to the power 2 pi I. And now j is equal to 1, right? This is equal to j, and this is equal to j. So here you get a 1, so this doesn't disappear this time, and the k divided by 2. So for k equals to 0, it disappears again. So the 0 state remains the same. For the second, you get this exponential phase factor, e to the 2 pi I over 2, 1 over square root of 2. And what is this thing? This is just e to the I pi, right? So I'll sin a bit and use a blue pen here. Hopefully it's visible. E to the I pi is equal to minus 1, right?
Sorry, just something about the notation.
Yeah.
So the I is the complex.
That's yes.
Okay.
Absolutely. So I should probably have mentioned that, but yeah. So e to the I pi is equal to minus 1. So you end up with 0 minus 1 over square root of 2, which is once again the Hadamard transform of the 1 state. So what I'm saying is that the Hadamard transform is actually just the 1 qubit Fourier transform. It's the same thing. Okay, so far so good. Maybe I can summarize up here by saying that 0 being Fourier transforms becomes 0 plus 1 over square root of 2, and 1 Fourier transformed is 0 minus 1 over over square root 2.
Mhm.
Okay, so with that in mind, may I wipe?
Yes.
All right.
Yes.
Actually, this one I'd like to keep. So I'll put a square around it so I don't forget. Okay. I'm going to go up to the 2-qubit case and do one of the transforms there as well, just to see what we get. And now I'm going to need my notes because, well, I can probably do it without still, but so I notice if I fuck anything up. So the one I'm going to transform today is the state 0, 1. In a 2-qubit case, so F. Now this is square root of 4, so 2. And it goes from k equals to 0 to 3. E to the 2 pi I 0, 1. I mean 0, 1 is the same as 1, right? So times 1, I'll write here just for clarity, and times k over 4. Okay. So we are going to get sum of 4 terms. Let's look at what they become. So for the first one, it's easy because that's k equals to 0, so the entire thing disappears. So that's a 0, 0 state in binary. Second one, e to the 2 pi I over 4. Now k is equal to 1, so that doesn't count anymore. I'll just immediately cancel the 2 and the 4, so we get I pi over 4. No, over 2. That's supposed to be over 2. Sorry. I pi over 2, 0, 1. For the second one, we get, no, that's a 0, 0, 0, 1 plus 1, 0. So that's 3 over 4. So it ends up being I times 3 pi over 4. 1, 0 in binary. And the last one is, no, I'm doing this wrongly, am I not? Let me
No,
just.
the third one is not correct.
Yeah, because this was supposed to be 1, but that's 2.
But it
2 times.
No, it's 2 times 1, right? Divided by 2. This is correct.
This is oh, okay,
Yeah,
yes.
but
And
it's
then
not-
yeah, because
yeah.
so this should be over 2. That's the mistake. Is that okay? And then for the final one, we have
This middle one is
yeah. There's something. It's not
no,
right.
2.
Yes.
I think it's just
2 times
pi
2
I,
over
right?
4.
So it's pi I.
Yeah.
Yeah.
Yes. That's a mistake. And the last one, there we get the thing I was trying to write down.
Yeah, 3, 4.
3 pi over 2. That makes way more sense. Thank you. Okay, so each of these, what are they? Well, this is, let's use the blue one again. This is equal to -1. Fine. I pi half. So I keep thinking in regards to the real imaginary axis, right? So pi half is 90 degrees. This is the real line and complex line. So 90 degrees up here, then you get that this is equal to I. And for 3 pi over 2, then so this one goes here, so that's equal to -1. And 3 pi over 2 is down here, so that's equal to -I. Good. So what we get in the end is a sum like 0, 0, 0 plus I 0, 1 minus 1, 0 minus I 1, 1. Agree?
Yes.
Okay. So the rest are computed in exactly the same manner. So with this in mind, I'll just write up the result of each of them, and then we'll have a look at what we get. Yeah, so the first one is straightforward, which is why I didn't want to do that one. Let's just 1 over 2, and then each of the basis states summed. Second one is the one we just looked at. So then that gives 0, 0 plus I 0, 1 minus 1, 0 minus I 1, 1. Third one. So I'll wipe this. So it's a lot of writing, but I promise I have a point with this. This becomes 0, 0 minus 0, 1 plus 1, 0 minus 1, 1. And the final one uh, 0, 0 minus I 0, 1 minus 1, 0 plus I 1, 1. That's the two qubit basis states transformed. So the thing that I kind of want you to notice about these is that once you see how these work, you can actually get an intuition so that you don't have to do this explicitly, these calculations. You can kind of just look at the basis state and then immediately know what the Fourier transform has to be. Because in the 0, 0 case, if we look at this complex plane again, you are, for each of them that you are counting through, you are just staying here. You're not going anywhere in the extra phases, I mean, that go in front of them. You're just staying on the one spot. So I'm saying that if I call it delta theta, meaning the size of the angle for each step is equal to 0 in that case. While in the 1, 0 case, you get something more interesting. Because then you see that you are moving first here, you're always starting there, and then up to 90 degrees, and then down here, and then down here, and then you're kind of back, then you're done. So here I would say that delta theta is equal to pi over 2. And similarly, for this one, you see that you're just going here, and then over here to the minus side, and then back to the plus side, and then back to the minus side. So for the 1, 0 state, I would say that delta theta is equal to pi. And for this one, finally, you start here again, and then you go all the way around till you reach the minus I point, and then all the way around till you reach the minus 1 point, and then all the way around till you reach the I point. So in this case, you're going 3/4 around the circle, which translates to 3 pi over 2. Does this make sense to you? So this is not something you find in the book. This is the kind of intuition I have built up for myself. And we would like to know how this kind of picture generalizes. So I'll do like this, and 0, 0 has a delta theta of 0, and 0, 1 has a delta theta of pi over 2. And then I'll wipe a bit. So here's my recipe for Fourier transforms. Whether or not this recipe is actually useful, I'm not really sure about, but at least it's useful for like a mental picture of what's going on. So for an n-state basis, meaning that you have n qubits, divide unit circle up in equal slices of delta theta equals to 2 pi over n. So in this case, we had n equals 2, so you see you get 4 slices with each of with pi over 2 or 90 degrees. So for a for a 3-qubit state, you would get a picture like this, where you 2 pi over n 2. No, that does not make sense. Let me think. I think this is supposed to be capital N. So you get 2 pi over 8 equals pi over 4 equals delta theta. Because then you get the kind of picture here, right? So you get a pizza of a sort. And then for the 0 state, you just go through them while remaining here. For the 0, 1 state, you clock through them going clockwise 1 step at a time. For the 2 state, you go 2 steps at a time. For the 3 state, you go 3 steps at a time around the unit circle, and then all the while multiplying the resulting phase in front of the basis states. So I'll see if I can formulate this. So construct J prime from J by starting at theta equals 0 and moving around unit circle by steps of J times delta theta. So this would be J times 2 pi over capital M. And then multiplying each basis state with resulting phase and summing the results. So that's my recipe for general quantum Fourier transforming in your head or on the back of an envelope or somewhere else that's where you don't have a lot of space. Can you read what I'm writing? Right?
Yes, yes.
But I'm actually, maybe I'm not really following your logic, but is that just by definition?
This is by observation, more or less.
But this is definition, right? Because how you get delta theta actually follow the definition, right?
Yes, I mean
because you just rewrite the delta theta like this, and you can put that in the definition, right?
Yeah, I mean I could say that this is equal to. Is that what you mean? Like delta theta
times something you want. Then this
times ijk.
Yeah, so then this follows the definition what you say, right? Construct J prime from J, this actually from the
Yeah.
I guess it's just more of an geometric interpretation of the statement in a sense.
Yeah.
Which is nice because as you said, I don't think the book really delves into it, and certainly Matthew didn't do it in his course. So then it's kind of like, you know, if you haven't brushed off your trigonometry, I guess, then yeah, then this formula is quite esoteric. So yeah, I think it's nice with this. Picturesque approach.
Yeah, this is how I think, right? In order to understand the formula, I need to know what it's doing. So you're quite right. They are equivalent descriptions.
But I'm just wondering whether there's a more faster way to calculate this, or I don't know, or to see. It seems that we still need to.
I think actually I need to spend 2 weeks on this because I plan to go through what the book is saying as well.
Yeah.
But in order to show that, I will have to give you my intuition of what's going on first.
Yeah.
But there we will see a rewriting, like an alternative formula that is very powerful, I would say, and that you can also that also takes a lot less time than to calculate this explicitly. So I think maybe that would be the one you're looking for. And if we have time, I'll come to it by the end of today. But that depends.
But the other question to me is that, to me, usually, actually, they should have some meaning why they define this, right? Because when we talk about classical Fourier transform, actually, we do have a quite engineered meaning for this. But I'm just wondering why this, I mean, circular things, and they mean, why they can define this called quantum Fourier transform. I'm just wondering.
I mean,
from which domain? Actually, they are not mapping different domains, right? So, if I remember correctly, the Fourier transform in classical is that you transfer things from time domain to the frequency domain.
Right. Or
but here it seems to me you didn't transfer anything. You just do some rotation.
Well, it implies the kind of transformation you were talking about, because these are frequencies, right? If you let one of these, let's say k, for instance, be equal to the time, then this transformation will take a function of time and give it out a function of frequency instead, I believe. Or it's the same thing in classical mechanics. It would be the same as transforming from Euclidean space to momentum space. And I believe there is a correspondence between the two because momentum is equivalent to frequency due to some quantum stuff.
Yeah, but here, I mean, my question is more mathematical. Here we just mapping the domain from 2 to the n to still 2 to the n, right?
Yeah.
Because it nothing changed the domains.
No.
So I just wondering why they define this. My point. Of course, I think exponential is exponential 2 pi times I. This shows up, of course, in the Fourier transform. But I just wondering.
Yeah, I mean, if you just remove the brackets here, you get the classical.
Yeah. No, I think not. If, for example, if you have some function of t here, and they map the other function called function big capital F. So they basically transform time domain to the Fourier transform to frequency domain.
Yeah, but I believe it's still the same formula.
No, I think that, I mean, of course, there are many, but my point here is that they transfer from time domain to frequency domain. So basically, two different domains.
Yeah.
But here they're still in the same domain.
That depends entirely on what you mean by domain. Maybe if I get to continue, maybe some of your questions will be answered by my next point.
Yeah.
About why we would want to do this. Because
That's my original question. Why? I mean, they define this. Seems to me not so clear that even if they just transfer to the same domain.
Okay. So I'm going to wipe out my very nice recipe now, if you don't mind.
Yeah, I can.
Yeah. Because I need some space to continue and hopefully answer some of the questions. So one of the main issues with the kind of question you're asking is, of course, that we are not really talking about the time and frequency of these states, because that would imply starting to talk about Hamiltonians and stuff, which is what people who worry about how to build these things spend a lot of time thinking about. Or if you want to simulate quantum physics, you would also spend a lot of time thinking about it. But for now, we have kind of discretized time, right, with these time steps and circuit depth and this kind of thing. Anyway, so primed states are now the states that have been Fourier transformed. Okay. So what I want to show is something pretty straightforward. So 0, 0 plus minus I 0, 1 minus 1, 0. Now I keep writing this the wrong way around. Plus I on 1 times the old thing So I want to multiply this out, and we know that the old basis states are also normal, right? So these two together become 1, while this times any of the others just becomes 0. So all we have to care about are the ones that are lined up here. And multiplying it together, we get 1. So this is minus I squared, so that becomes a plus 1. Minus times minus is also a plus 1. And here we get minus I squared again, plus 1. So we see that this becomes 1. Okay, good. It's normal. No, it's it has magnitude 1, which is a good thing. And then checking it together with a different basis state. So let's take the trivial one. You get 1/2 0 0 minus I 0 1.
Is that the Fourier transform just a unitary transformation?
It is a unitary transformation, yes.
Then this should always hold, right?
Yeah, I believe so. I mean, if it wasn't a unitary transformation, then you couldn't implement it on a quantum computer, right?
Yeah, but I mean, then this inner product definition just given 1 by unitary transformation, right?
Yeah, that's true. Anyway, doing the check still can be useful, just to see that we've done everything right. So this becomes 1 minus I. Yeah, this becomes 1 again, so that's fine. Minus 1 and then plus I. So this is equal to 0. So yes, since it's a unitary transformation of basis states, the entire point is that what you get is another set of basis states, right? So you get the kind of situation where you have J and K is equal to the Konica delta of J and K. And that holds after transformation as well. So that's kind of the point. You're just transforming from one basis to another.
Yeah.
Okay. Right. So there is one more question which presents itself, which is what happens if you Fourier transform a state twice. First of all, so Fourier transforming into a different state, you would kind of hope that by doing it one more time, you get back to the original state, or original basis at least. And so I'll just quickly show what you get. Yeah, I think I can wipe this now. Because I spent a lot of time on this, on trying to figure out what happens when you Fourier transform something twice, because in Simon's algorithm, Simon himself says that he is Fourier transforming twice. But working through the steps, my results didn't match his at all, until I realized that he wasn't Fourier transforming twice. He was doing the Hadamard transform simply on all of the qubits, like this, which is not the same as a Fourier transform. This is just putting the Hadamard transform on each single qubit.
Yeah, that's my actually wondering. So, what's the main difference? Because now so far, I mean, of course, in the future,
okay,
maybe you will talk more. But so far, the Fourier transform is more like a unitary transformation for me. So
it is a unitary transformation.
Yeah, but I'm wondering what's the difference between doing this and then you do Fourier transform n times, for example.
Yeah, right. Because for comparison, I do have this formula here. Just since you asked. And this actually ends up being, so first of all the phases are either 0 or are either +1 or -1.
Yeah.
And it's dependent on, so in this case I should write, for this to be correct, this should be a J here. So if you take like the inner product, the bitwise inner product, I guess, or the XOR, I guess, of the J and the K. So to bring this into proper computer science language, we should probably write it like this. And if this bitwise inner product is equal to 0, then it's a positive phase, and
Yeah.
it's equal to 1.
And it's never like I or J or something.
No, this isn't right. The XOR becomes wrong. I don't know. Okay, in bitwise inner product anyway. Yeah.
So I mean, there's no compressed number shows up.
No, this is if this is real, then this is real.
Yes. Yeah.
So that's in stark contrast to the more Fourier transform. So this is the one that Simon employs in his algorithm, right? Which if you had 4 qubit, 4 qubits here, you would write this circuit with individual ages. Well, for the Fourier transform, you really can't do that. Then you would have to do one big block, because then every state influences each other and mixes in a more general manner. But still, this is also a unitary transformation, so you still go from one set of basis states to another set of basis states. It's just a different one. All right, I wanted to answer the question, what happens if you Fourier transform something twice? So I'll use this notation because that's what I used when I investigated this. That's f of j. So just inserting the formula, we get k equals to 0 to n minus 1 e to the 2 pi I j k over n k. And so obviously I can take this f inside of the sum and everything, and let all of this be outside. I j k over n, and then f of the basis states k here, which gives me a double sum. Okay, I'll do every step, I guess. So e to the 2 pi I j k over n, and then just one more time, L equals 0 to n minus 1 e to the 2 pi I k L now, n and L. So double sum with capital N here, k equals to 0, n minus 1, L equals to 0, n minus 1, e to the 2 pi I k is factored out, and you get j plus L inside over n and L. And now we have this very nice, identity somewhere around here. Ah, here we are. So I'm going to use the following identity, that delta mn is equal to 1 over n, k equals 1 to n e to the 2 I k n minus m over n. So we see that this looks very much like what we have down here, just if we let n be equal to j and minus l be equal to m. Well, in my notes I did it the other way around, so let's stick to my notes. The 1 over n disappears as part of the definition. One of the sums disappears, and we are left with the sum L equals to 0 to n minus 1 of Kronecker delta minus j and L of L. So the way Kronecker deltas work, of course, is that when you sum over all possible values, you are just left with the ones that are equal to 1, and all of the ones that are equal to 0 just disappear. So the point being that L becomes equal to minus j. So you now have a state minus j as the output, where j was the input. And of course, since everything is modulo capital N, you can rewrite this in positive terms as capital N minus j. So you see, we don't get the same states back. For instance, if I input 1 here for a 3-qubit system, I will get 7 back. And if I input 3 here for a 3-qubit system, I will get 5 back. But I get the same basis, right? It's still the same basis states, namely the computational one from 0 to 8, not from 0 to 7. So yeah, that's what happens if you
even for classical, it's not. If you apply Fourier transform twice, it's not get back to the original state, right?
If you're interested in what?
I mean, if you apply classical Fourier transform twice, we are not end up in the same thing, right?
Well, I believe you should, meaning that if you Fourier transform a set of data twice or a set of something, you should get back the same set.
No,
but the same element doesn't map to the same element.
Yeah, that's why there's something called inverse Fourier transform, right?
That makes sense. Yes.
Yeah, that match the time domain to frequency domain and match back.
Yeah, but if you keep going instead, I believe you will get back to the time domain, but in a slightly different manner than if you do the inverse.
No, I think that's different concept, at least from classical.
I mean, if you Fourier transform something that is already in the frequency domain, you would expect to get something in time domain.
Yeah, but they are not called this transform as same as this Fourier. They call it inverse Fourier transform.
Yeah, but that's because it's a
they have a different definition for inverse. So basically, they have f function and also f inverse function.
Sure, and
so by here we are not doing this, right?
Because here we are going forwards instead.
Yes.
But you are still going back to the same domain, even if the elements don't map onto the same elements.
Yeah, but this is because we all mapping in the same domain, right?
I'm still skeptical about that claim, because I'm not sure if the sense of a domain, I'm not sure if the domain you're talking about makes sense in this setting.
No, of course. So that's why I'm confused. But I just want to know the fundamental difference between classical and quantum. What's the difference? Why they have this? And it seems now to me everything just mapping in the time domain.
I think you should stop thinking about the time domain at all. I'm not sure that makes sense to talk about here. I think that if you inserted a bunch of Hamiltonians here that described each qubit individually, you would see that you would actually map from a time-space domain to a momentum frequency domain.
But not this definition, right? So I mean, so far this definition.
Well, if you make this continuous and you put an integral here instead of a sum, then yes, this definition.
No, even if with sum, we still mapping to the time domain by even you do integral, right? I'm not sure what's the integral version of this, but if you check the wiki, right, the discrete Fourier transform they will have a time domain, say xk, small sk, and the frequency domain, big sk.
Okay.
So they have this mapping with time and frequency. But here, I mean, my question is just, they don't use this.
Well, I don't know. Okay, so the way I know this from like continuous stuff is that you map from a 4-dimensional time space to a 4-dimensional momentum space. And I believe that quantum mechanically, this is equivalent to a frequency space. Because you have stuff like the energy, which is one of the 4 components of this, is equal to h bar omega.
Yeah, so this
is
so this is more nature to me to what we mean Fourier transform, right? Because basically we from the time domain x and then mapping to the some, I don't know, p domain. So this is more, but here I still not.
Okay, so I think it's hidden in the description of the individual qubits. So each qubit can be described, can even be defined, I believe, to be some integral with some Hamiltonian over some 4-dimensional psi, and then you get this. I really don't remember right now, but you get something like this, and then doing a Fourier transform, which would then have to be continual, you would get a momentum space description of this quantum state.
I see. Yeah, I think this is part. I mean, at least from the physical part, what I'm missing here.
Yeah, but I mean, this is. I believe it's the same formulas, like they are equivalent up to the discretization, but it's now used on information instead of on like physical variables or observables, as you would call them, right? It's used on the data here, which is the main difference. Correct me if I'm wrong, but it doesn't seem to me to make sense to transform data from a time to a frequency domain unless that data has a specific interpretation.
No,
as a signal, for instance.
Maybe we, because we are learning from different paths, but at least because I did learn Fourier transform first. So that's why I talk is more what I know about classical Fourier transform. So
right.
I'm just wondering if they call this quantum Fourier transform, they should have something similar. But so far, I just don't see this similar thing.
Yeah, okay.
Or they can say, I don't know, Fourier unitary transform, but not call. I mean, I just want to make sure whether why when they introduce this name, they should have some reason, right? And
I think that what you would find is that if you.
But I think this point is more makes sense to me because in classical Fourier transform, they can show that the energy in the time domain is equal to the energy in frequency domain.
Yeah, that makes sense.
Yeah, so this is the basic property of the Fourier transform.
Right.
So why you show that part actually makes sense to me.
Yeah, this.
Yeah.
Right. So in case you're curious, by the way, when you're transforming between these domains, so you have x, y, z, and t. when you do a transformation to the so-called frequency domain, these become the three axes of the momentum, while the t becomes the energy. And then if you calculate calculate the energy here, you will find it to be the same one as here. That's the kind of, when we did quantum field theory, this is the kind of stuff that we will do all the time. What I was going to say is that I think that if you input a bunch of data that has the interpretation of being a signal as a set of states, and then do a quantum Fourier transform on it, then your interpretation will start making sense again.
No, but that's maybe this is the question. So what's the point to do the Fourier transform, right? I mean, in classical everything engineering really makes sense. You just transform from time domain to frequency domain. This makes sense because this signal processing is.
Right.
But I'm just wondering, okay, then what's the purpose? If we don't map the time domain or quantum states to the other domain, then what's the purpose to here that they do this quantum Fourier transform?
I think this. I mean, the Fourier transform itself is used for a lot more than just signal processing, right? In mathematics, and I think this is one of those cases where the ends kind of justify the means. We have already seen that this will lead us to a factoring algorithm, for instance, and a similar one with the H cross N led us to a period finding algorithm.
Yeah, so that's I just want to go into say that, or maybe we should not think they are similar. Maybe they are just two different things, but they have a similar mathematical definition. But of course, the engineering definition is not related.
Well, if two formulas are the same, then they are the same concepts in my head. But maybe that's just a mathematical part of me speaking.
Yeah, but mathematical idea, everything is the same because by definition they can use this. But I mean, at least from the signal process point, the Fourier transform is quite makes sense because we can do this time to previous domain, and everything becomes easier because you can do a spectrum analysis.
Yeah, but I mean, with other data, other stuff also becomes easier. It's not just in engineering and signal processing. So I think it's just the way I look at it, and of course, this is one of the reasons why I kept being confused by the Fourier transform, because I couldn't always see why we did it.
But, so I mean,
in signal processing, it's really hands-on.
Right? Yeah, it could quite make sense.
So here it's just a transformation of data that has a lot of really nice properties.
Yeah, I think putting this way is more makes sense because so far I just don't see the engineering meaningful this.
Right.
This is honest. Yeah.
But again, we are working with information here, pure data, right? As computer scientists, that doesn't necessarily have a specific interpretation. But
I think at least this is why I learned. We should not always just think math because some good work they actually have very good engineering meaning because
that's true.
And I believe these researchers they are not just mathematicians, right? So they should have some. I mean, maybe we will find out later, but I believe they should have something.
Let's put it like this. The thing you're saying about the space domain, time domain and the frequency domain, I view that as kind of a special case.
Yeah, I think I see you seem like a special case.
Yeah.
But maybe when they or when we talk about applications, things will become clear. That's my.
Yeah, I'm hoping so. And I haven't prepared all notes, so maybe I'll find some surprises myself and know more by next week. Anyway, I did have some more stuff I wanted to say. So this stuff about double Fourier transform, of course you can always define an inverse Fourier transform since all unitary operations are easily invertible, invertible by just doing the diagonal. In which case you would also get back the same basis states, but then each state would actually map to itself, of course. But I just found it interesting, or kind of reassuring at least, to know that doing it twice also gives you back the same basis, even if they don't map onto themselves.
I mean, F4 is the identity, right?
Is it?
Doing
I didn't.
Fourth would be the identity, wouldn't it?
I guess it would. I mean, if you do this thing twice, then you get kind of like, you get, that's true. You get to like a minus j.
Yes.
So, yeah. So that's F4 of j. Good point. I didn't catch that one. So now we know.
Now we know.
All right. Next on my list is how to implement it, like looking at the circuit itself. And now I kind of come back to the book of Nielsen and Chang and start looking at what they have to say about the Fourier transform. So all of this stuff was stuff that it's just results of me playing around with the formula, more or less. So, what time is it? Yeah, we still have some time. I'm going to start off by doing a familiar thing for computer scientists, at least, which is to define the bitwise expansion of a number j, like this, where each of them are defined as 2 to the n minus 1, where j1 is now the most significant bit, right? Plus all the way to jn being the least significant bit times 2 to the 0. Do you agree with this definition? Yeah. So when Nielsen and Chang talk about the Fourier transform, they use this a lot. So they have quite a different intuition. Oh, it's actually I'm always almost out of power. Maybe this will work. Ah, yes. Very good. So when Nielsen and Chang talk about the Fourier transform, and this is why part of the reason why the book confused me on this topic, because I'm not used to thinking about bitwise expansions, but they do come up with some really nice formulas through using this thing. So let's just go through the derivation of this very nice formula. One over square root of n n minus 1 e to the 2 pi I j k over n j, no, k. Okay, so first thing they do is that they say, well, we can expand this k in a bitwise manner, and then we just get the sum from 0 to 1, and then a bunch of sums, n of them to be exact. And then this becomes e to the 2 pi I j, and then we use this thing, k1 2 to the n minus 1 plus up to kn 2 to the 0. And then it's divided by capital N up here, but now I'm going to write that as 2 to the power n. And similarly, for the end state, we do a bitwise expansion. Okay, first thing we do is we split up this and this. So the start is the same, bunch of sums, k n equals 0 to 1. And then the first part here multiplies with the first part there, e to the 2 pi I j k 1 times 2 to the minus 1 k 1. So this 2 to the minus 1 comes from the fact that here you have 2 to the n minus 1 and divided by 2 to the n. So you end up with 2 to the minus 1 here. For the second, you get 2 pi I j k 2, 2 to the minus 2. Similarly, you have 2 to the power n minus 2 divided by 2 to the n. That should be enough to see the resulting pattern, right? So you get e to the 2 pi I j k n 2 to the minus n k n, like that. Which means that this can now be rewritten in a more compact way. Still with all the sums though. So now we get a tensor product, a big one, for L equals 1 to n, e to the 2 pi I j k L 2 to the minus L. And finally, here you have a k sub L. And then we observe that these can be put inside of the tensor product for an even simpler notation. Big tensor product of L equals 1 to n, sum of k L equals 0 to 1, and e to the 2 pi I j k L 2 to the minus L and k sub L. And then we simply calculate this sum here, where you see that if KL is equal to 0, then this whole thing disappears. And if KL is equal to 1, then it stays, but the K disappears, of course. So this becomes 1 over square root n. L equals 1 to n. 0 plus e to the 2 pi I j 2 to the minus L k sub L, which gives the final formula. And this is the one that I talked about earlier that might be actually the easiest way to do all of this.
Yeah, since this is more easier.
2 pi I j over 2 1 0 plus 2 no. So easy to make mistakes when writing these formulas. E to the 2 pi I j over 2 to the n 1. And then this entire thing is divided by square root of capital N. So the only thing that changes between all of these products is that this 2 here, I should write 2 to the power 1 here, I guess. You start dividing by 2 to the power 1, then 2 to the power 2, etc., up till you divide by 2 to the power n up here. Can you see properly, or am I sitting in the way?
Yeah, I see. So what happened with a K in the last step?
Actually, it disappeared here, and I miswrote here. This is supposed to be 1. Yeah. Because we just calculate this sum, KL equals 0 to 1. So that's just 2 terms, and one of them is without a phase, and for the other one you get this phase.
Ah, yes.
And then I expand the product again, and we get all of these parentheses. So with this formula, you could, I mean, the input state is J, right? And you know what the binary expansion of J is. We should probably, did I forget something here? Ah, no, actually, we didn't use the binary expansion at the end. Ah, yes, I'm coming back to that point. That's why I'm confused. But yes, you could, in principle, just input J here and get the correct answer straight out. So I'll keep this part and wipe the rest. And then say that J Fourier transforms becomes this. And since it's equivalent, the book makes a case that this could actually be taken to be the definition of Fourier transforms. Yeah. So wiping all the algebra away. So now it's now out of notes, but I'll go on for a little bit anyway. Let's see if I can. Let me think for a minute. I don't know. Okay, so this part is still confusing me a bit, but maybe we can figure it out together. So they are saying that we should adopt the notation 0.JL JL plus 1 up to J M to represent, so by definition, this is the binary fraction. So I'll write that there, binary fraction. That's binary expansion. And this represents JL over 2 plus JL plus 1 over 4 plus up to JM over 2 to the power m minus L plus 1. And I guess that's just because we're starting at L here. I think what confuses me about this is exactly what it represents. Like, what is the fraction that you would put here that leads to this number? But I guess that's not the point right now. It's just a notation.
So how's it used? Did you say? I mean, like this is just a definition, right? But kind of how it works.
Because you can see that here you have j divided by 2 times j divided by 4, j divided by etc. etc. And then you can really use this formulation to insert these binary, so not decimal points, but binary points, I guess, would be the translation.
But could you write out like exactly how it's used in this case?
Yeah, that's the next step.
Oh yeah.
The final formula that they write is 0 plus e to the 2 pi I 0.jn 1 dot 0 plus e to the 2 pi I 0 dot j1 to jn 1 and square root of capital N.
Okay, 0.4.
So in order to just be clear what goes where, we're saying that j over 2 is equal to 0.jn. While yeah, you see why this it's good that I'm not the only one who is confused, actually. That feels good. So j to the divided by 2 to the power n is 0.j1 dot 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 jn.
Okay, I see your point.
So it kind of makes sense to me, but not entirely. Because
So what's the difference between that and that? It's just j, right?
I mean, it's just a different way of writing it, but the way that they developed the quantum circuit, it really becomes easier to see it this way.
I mean, compare the above expression and the bottom expressions. It's just different from 0.jn and here j divided by 2, right? And this is everything just by definition, right?
Yeah.
So it's equal, right?
Yeah, these are equal, definitely.
But then what's the issue? Or you mean why they use this definition? Or
yeah, I'm trying to get my head around the result, because if okay, so here's my question: what if j is equal to 3? Right? Then so in binary, this would be like an endless thing. No, in not in binary, but in decimal. So what happens if we do it in binary? Then it becomes 101. No, that's not true.
1, 1.
Yeah, 0, 1, 1 divided by 10. Okay, yeah, I guess I guess that kind of makes
Yeah,
sense because you get 1, 0, 1 times 0.1. So this thing is Jn
yes.
in that case. Is that true? I guess.
It's 2, right? Why 2 divided by 0.4? No, but we should use that definition, right? Binary fraction is 1.
Yeah, but so where does this part go? Do you only care about the part behind the dot? I mean, maybe this one just goes away because 2 to e to the 2 pi I times 1 is
Yeah,
1.
I think that's just by definition of this kind of things, right? The binary fraction definition.
Mm. Okay,
So we need to write down by definition this, and then we can just match and find a GN.
so this is one of those cases where I would have to sit down with pen and paper and just spend 30 minutes playing around with the definition. So I would suggest picking up again next week from here.
Yes.
And then by then I would probably have a better understanding of what the hell binary fractions are and how they work. I mean, intuitively, the concept makes complete sense, right? It's the same as decimal fractions, just binary. But getting my head around it is a different matter. So especially the part about being able to just throw away everything in front of the dot seems to me to be, it's possible that it's because of this e to the 2 pi I equals to 1 thing. But I would have to check that and see that everything still makes sense, so I don't start spewing lies to you.
So this break, okay, yeah.
All right. Any questions so far?
Yeah, that's a question. But
And
I mean,
did I go too slowly or too fast? Did I bring too many details or?
no, I mean, my question is what I think about.
It was good.
But everything is good about this, but I mean,
The intuition about why we do this.
I believe as long as we learn more, we can have more better.
Yeah, because the short answer is I don't know why we do this, but I do know that it leads to good things.
Yes. But I guess the other question, whether they just use this for shows algorithm and or algorithms, or whether they use this in other parts. You know?
I have.
Or they just use in the shows and Simon. I think Simon also.
It's used for. I mean, it's used for lots of stuff, but it's among others. Shows algorithm, which is both factoring and discrete logarithms and finding hidden subgroups, definitely use this. Other than that, Grover's algorithm does not use it. That's a simpler algorithm in a sense. Actually, it's simpler to understand, but more difficult to see how he invented it. Of course, whenever you want to try to design an algorithm with an exponential speed up, this is kind of the first place you go, because compared to using the fast Fourier transform on exponential size states, it is exponentially faster, and it's so versatile. It seems to be kind of like the main tool in the box for exponential speed up algorithms. Of course, there are many quadratic speed up algorithms and stuff like this, including Grover's and Simon's, and well, Simon's was actually, that depends as far as I recall. And those quadratic speed up algorithms usually don't use Fourier transforms. But I don't know, if you want to do like quantum physics simulations, for instance, this would be extremely relevant, which is the other big use case, right, of quantum computers.
Yeah, I just wondering what's the...
Again, I mean, I really don't know. It's interesting to ask the question about whether it's used in like communication protocols and entanglement creation.
I don't know, quite key distribution. I don't know.
Yeah, because there is the end result here is a highly entangled state, right? So whenever entanglement is a resource that you want to use, I mean, then the most common thing to do is, of course, this thing. But as we've seen, these are closely connected transformations, so there might be cases where this is more relevant, but that's an interesting question. And also, by the way, I should mention that, Isam said that if we are thinking about doing some quantum information, but also communication, like communication protocols. So quantum key distribution is one thing, and we might go through the basics of it, but it's pretty straightforward and it doesn't take long to understand. And in my opinion, it's not that interesting, but there are a lot of other very interesting protocols in communication. And networks and such. So at some point, he at least really wanted us to talk about that.
I see. Yeah, that's great.
Yeah. And also at some point you need to present the things that you
I think that part is more related to
storage, was that it? And
no, it's more related to quantum information.
Yes.
Also, I think that's also what some.
And the von Neumann states and all of these things.
Yes. But I mean, at least.
At some point we should have like a thorough introduction to density matrices.
I definitely want this because I have no.
I can do it, but then it would be very much in this style. I'll just.
No, but that would be good because I think, from my point of view, I just use it.
Yeah.
But I would like to know the physical why they use this.
So one very interesting fact I know about density matrices is that you could formulate all of quantum physics in terms of density matrices. You don't actually need quantum states.
This was introduced by Charles Bennett, right? I believe he had a very good physical intuition. Why they use?
I mean, density matrices are a lot older than him, I think.
They could somehow interpret entropy by these things in quantum field, right? And once you don't care about quantum, you just reduce to classical.
Yeah.
I think it's quite interesting, and I want to know why. More physical part, to be honest.
Definitely interesting because
if we just compute, I don't think that's too much difficult because.
I mean, seeing some basic examples and some, and especially this quantum to classical correspondence might be easier with density matrices because they kind of become probability distributions.
So
and once you see how a certain density matrix becomes a Gaussian, then
maybe some feeding about this thing.
Hopefully. All right, but I guess I'll continue this next week and try to get to how Shor's algorithm uses it. But it's like a several step process because the quantum Fourier transform is used for something called phase estimation, where you're trying to where you're efficiently estimating the phase of a state. And then this again implies some solution to a number theoretical theorem, which again implies a solution to the factoring problem. So it'll take us a while to get to the end point, I think, but it will be good to go through all the steps very thoroughly because the book is a bit quick about it. So when reading it, it feels like, oh, you just lost me. All right. Happy?
All right. Yeah.
I think we can just continue.
It was good.
Yeah. So I shall stop the recording in 3, 2, 1.